Okay, we talked about, we derived the beta distribution last time, in terms of as the ratio of the relative size. So the beta distribution was the relative size of two independent gamma random variables, as we showed in this example here. And we derived its density in this way. What I want to do now is just to kind of show some relationships or some related distributions to the beta. And so some of its properties. Okay. So first of all, what can we say is the number one, as we've already seen, but an important consequence is that if x and y, if x is gamma alpha lambda, y is gamma beta lambda, and x is independent of y, then we've already shown that x divided by the sum of x and y is beta, and the parameters are the shape parameter of x and the shape parameter of y. Second observation is that if u is uniform 0, 1, then u is beta 1, 1. We can see that directly from this density, because if you put 1 in for alpha, this becomes x to the 0. 1 in for beta, this becomes 1 minus x to the 0. Those go away as 1. Gamma of 2, which would be gamma of alpha plus beta, is 1. Gamma of 1 is 1. So this whole thing is just 1 on the unit interval. Okay. Okay, if you let x have a density given by 2x on the unit interval, so it's linear in x with the normalizing constant 2, this corresponds to the beta distribution with parameter 2, 1, right? Because x, the key part involving x is x to the power 1, which would be alpha minus, well, x to the alpha minus 1, which requires alpha to be 2, and then we have to get rid of the 1 minus x by putting in a 1. Okay. If we have IID uniforms, NIID uniform 0, 1s, and we let x be the kth, x be the kth smallest, of u1 up through un, then what is the probability that the kth smallest is exactly x, right? So we're thinking about, this is the probability that x is very close to x. Well, in order for this to happen, we need, what do we need? We need k minus 1 ui's to be less than x. We need 1 ui to be in x plus dx. We need n minus k ui's to be bigger than x plus dx. Once we pick which ones are going to be in those bins, right? So That's just the only way for the kth smallest to be close to X is if we have K minus one of them here, one of them here, and the rest here. But they're independent and they're uniform, right? So first of all, how many orientations are there? Well, there are. We need N, choose K minus one in one bin, one in one, and N minus K in the other. X to the power K minus one for the K minus one that are going to be less than or equal to X. DX for the one that's going to be between X and X plus DX because it's a uniform. So the probability of falling in that small piece is just the width of the piece. And then one minus X to the N minus K. As long as X is between 0 and 1. Well, if we redo this all, what we're left with is we have N factorial over K minus 1 factorial N minus K factorial X to the K minus 1, 1 minus X to the N minus K dx indicator 0, 1 X dx. Right, this is gamma N plus 1 over gamma K gamma N minus K 1 X to the K 1 minus X to the N minus K plus 1 minus 1. So this is X, which we've defined as U, the kth smallest U, is beta with parameter K and N minus K plus 1. Okay. If X is beta alpha beta, then what's the expectation? Well, the expectation by definition is the integral over all possible values of X. We weight X by its density. The density in this case is gamma alpha plus beta. So this is the normalizing constant. X to the alpha minus 1, 1 minus X to the beta minus 1 dx. The additional multiplication by X let's pull the constant out. So gamma alpha plus beta over gamma alpha gamma beta. The additional multiplication by X gives us X to the alpha, which we can write as X to the alpha plus 1 minus 1. 1 minus X to the beta minus 1 doesn't change dx. This is the kernel. This is the part. This is the key part of the density for a beta with parameter alpha plus 1 and beta. So in order to make that work, let's do this. In order to make that work, what do we need to happen? Well, we need to divide by, well, we need to multiply by the normalizing constant. The appropriate normalizing constant is gamma of alpha plus beta plus 1, gamma of alpha plus 1, gamma of beta. But we got to get rid of that, right? So we get rid of that by dividing, by inverting it. So we get gamma alpha plus 1 here, gamma beta, gamma alpha plus beta plus 1. Okay, Now what happens is once we've done that, this is the integral of the, this is overall, this is the all values, integral over all values of the beta alpha plus 1 beta, which means this is equal to 1 and goes away. And then our answer is expectation of x is gamma alpha plus beta over gamma alpha plus beta plus 1, gamma alpha plus 1 over gamma alpha. I'm just rearranging here. Keep things nice. Gamma beta over gamma beta. Well, obviously those cancel. But now remember the property of the, so recall, property of the gamma function was gamma of r plus 1 is equal to r times gamma of r, right? So in particular, gamma of alpha plus beta plus 1 can be written as alpha plus beta times gamma of alpha plus beta. Gamma of alpha plus 1 can be written as alpha times gamma of alpha. And this is just 1, so that goes away. And so now we have cancellation of the gamma functions, and what are we left with? We're left with expectation is alpha over alpha plus beta. So it's just the ratio. Again, it's the relative size of the parameters of the beta distribution. Exact same logic will tell us that will allow us to calculate the second moment of the beta. In this case, integral 0 to 1 x squared times gamma alpha plus beta. Again, the normalizing constant. X to the alpha minus 1, 1 minus x to the beta minus 1. Except the difference now is we're going to have an x to the alpha plus 2 minus 1. So what we end up with is, and I would leave this to an exercise to fill in details, but what we're left with is alpha times alpha plus 1 on the top, and then alpha plus beta plus 1 on the bottom. And then, of course, the variance of x, which is expectation of x squared minus the square of the expectation, which we already know. We know we've already computed these parts. And what we end up with is alpha over alpha plus beta, beta over alpha plus beta, times 1 over alpha plus beta plus